Hello friends, today I am going to show you and also explain you brief about SolidWorks simulation as well as what kind of simulations does SolidWorks include. So we will start with this. First, SolidWorks simulation has come with the different packages. In first SolidWorks CAD Premium, you get you will get the static analysis part as well as SolidWorks motion part, that is a motion analysis. Then in a simulation professional, you will get six type of six type of simulation: frequency analysis, fatigue analysis, optimization, which is a design study basically. Then a thermal analysis, drop test, and pressure vessel, as well as it will means these six simulation plus static and SolidWorks motion is also included in this package. And in SolidWorks simulation premium, you will get additional non-linear analysis, composite material analysis, and advanced dynamic analysis, plus these previous simulations. So basically in SolidWorks simulation premium, you will get all type of analysis which is present on this screen. Okay, so we will today we will start with the only static part, means static analysis introduction part. So first, the first question will come is ki, what is exactly finite element analysis? Now here one example is there. Let's say consider here one man is there, and here a mailbox is there. To go up to this mailbox, the man travel by this route, which is a curvature or let's say any random route. Now if I give you a roller and I said ki, you just give me length of this uh, whatever drawn path is there, then how will you do that? First you will put one roller here, then measure the first distance, then on the end of second point you will again uh, you mark that end point, then put a roller again it and again calculate for next. So you will do for all this path, and after that you will add all the all the segments which you have divided and give me the approx length magnitude. So basically what you did here, you just simplified this path, you measured by segment and then sum so, then sum or add whole the path and give me the result. So similarly, in FEA language, FEA basically finite element analysis. The name itself states that key it's a finite element, means how much segments you have divided, means how much segments you have assumed or created of this path is elements, and this number of elements means 1 2 3 4 5 6, how much time you measured that uh, length of that curve is called as a finite element. Means you know the number of the segments and you just simply add or multiply by that number of segments. So similarly in finite element analysis is a finite element means dividing your engineering or engineering problem into mathematical model with the help of elements. So its definition states that a finite element analysis is a mathematical technique for analyzing stress which break down a physical structure into substructures called finite elements, and these finite elements and their interrelationship are converted into equation form and solved mathematically. So this is a finite element analysis definition. Now, the basic finite element analysis poses three steps. Basically, first is a pre-processing, then solution, and afterwards a post-processing. So under pre-processing, what are the factors or what are the steps it includes is as follows. First one is your CAD geometry. Whatever your part or assembly is there, you will create it first in SolidWorks CAD module. After that geometry is created, you need to simplify that geometry with the help of defeature command or idealization process or cleanup tools. We will cover this in further simulation exercises. So your CAD geometry is a it's converted into simplified geometry, and this process is called as a idealization of geometry. It's not compulsory, but as per your problem statement, you need to simplify that geometry. After the simplified geometry, you need to convert that model into the mathematical. So for a mathematical model, you need to define four parameters. One is the type of analysis, means which type of analysis you need to do on that part, that you must be selected, that you must be selecting. In our further few sessions, we will dealing with only static analysis part. So we will do static analysis. Then afterwards, it's a material property. There are basically five material property you need to know for a static analysis. One is the yield strength, Young's modulus, density, Poisson's ratio, and ultimate tensile stress. These five parameters you need to know. After that, you will fix that part. Means before applying the problem statement, that part should be somewhere fixed in phase. Then loads, what kind of pressure, force, or any other load are acting on that part, which you need to check, that you need to apply. After these four parameters, you need to discretize or divide that CAD model into the mathematical model. Means you just mesh that model. Here you can see the triangle shapes are there, which are the small elements, that is the tetrahedron elements. The whole your solid model is converted into, or you can say that your small triangular element map the model for simplification or calculation. And up to this step, means up to discretization process, the steps which I have explained are come come into the SolidWorks FEA pre-processing part. After pre-processing, means after this machine, you simply run the analysis with the numerical solver, which is come under FEA solution steps. And after the solution is ready, SolidWorks whatever results you will get, you need to predict that result and you need to conclude from it. So which will come in SolidWorks post processing. So basically, in pre-processing, up to machine part will come. After that, for solution, your mesh model is only run, that's will be run to get a results, which will done by SolidWorks itself. And after post processing, which is it's completely depend upon user, and user will decide or conclude whatever, well, whatever whatever parameters are there. After that, in SolidWorks FEA model fixtures, here you can see is basically fixture. What it does, it only fix your model. Means if your model has to be fixed with some part, or let's say some fixture, so you no need to create that fixture or part separately. That fixture or part is directly replaced with the virtual fixtures. The fix, and where you can apply this fixture on surface, on edge or point. And you also apply siding, rotation, hinge fixtures, and fixture are used to reduce the size of the level or sub-assembly, because your computational time is very important factor in simulation. So there are same about the loads. Here you can apply the load. Here you can see this, the forces, means load. Let's say you can say that is a force, pressure, torque, moment, which you can apply on surface, edge or a point. and so these are the local, means here you can select the part or face for that force pressure torque moment. But some loads are like they are global. You no need to select a part or assembly, it automatically apply to the whole assembly or part, which are gravity, centrifugal force, and thermal loads. Now in FEA, as the name states, the element, it's a finite element. So here basically SolidWorks contain three elements in solid. Let's say in 3D, it's called a tetrahedral element. Here you can see the image of the small tetrahedral. Basically, the first is image indicates a draft quality mesh, which is means first order element. You can say that, which contain one, two, three, four nodes, and this is a pyramid kind of structure. And the second one is a high order, high quality or a second order, which contains 10 nodes. Means in between two nodes, one node is there. So these 4 plus 6, you will get 10 nodes. The use of this node is key. If you have a curvature kind of structure, then these node automatically get mapped to that curvature. And for a better result, we need to select a high quality one. But say for a solution, your time get slightly increase. And for this tetrahedral element, model has 3 degrees of freedom. Means it have only 3 translational degrees of freedom. No rotation is allowed here. After that, there are 2D elements, which is a plane linear triangular. Here also you can see two uh, two elements are there. Basically, this is a rough quality which contains 3 nodes, and this is a high quality. In between 2 nodes, you will get 1 node extra, which is 6 and 3. And here, degrees of freedom for your element is 6, means it contains all degrees of freedom. Basically, 3 translation and 3 rotation. And this basically come for a thin or a thick element, maybe like sheet metal part. You directly choose this shell element, and time required to run the analysis for shell element is lesser than solid element. And last one is a 1D element, or you can say a beam element. Here it's only one linear line with the 2 nodes, and it also contained 6 degrees of freedom, that is 3 translation, 3 rotational. And your beam structure or any weldment structure, it automatically treated as a 1D element. So in short, if this is your model, then small triangle, all are the mesh. Then the all small elements is there. In each individual triangle, you say it as a element, tetrahedral triangular, or and whatever junctions, means whatever joining these two triangular or corner of the triangular, you can set it as a nodes. And basically there are in general, you may heard in some or mechanics, there are 5 theories of failure, out of which 4 theories we will assume or work. Basically 4 theories SolidWorks assumes. First one is this von Mises stress. Basically, the stress at a point defined by 6 quantities. Here you can say that this is here 3 normal stresses as well as 3 shear stresses. The SX, SY, Z are the normal, while the TX, Y, TX, Z, these are the shear. So this is the formula. The zero point 0.5 under square root of zero point 0.5, the whole, this is the normal stress and this is the shear stress. So basically for ductile material, you can use von Mises stress theory or maximum shear stress theory. But in theoretical term, we go for maximum shear stress theory, which is 0.5 of your uh, yield stress. But for calculation, means in FES software, we go for one basis test, which is way give more accurate result than maximum shear stress theory, and it's used for a ductile material. while the other method is a maximum principal stress theory, where three normal stresses are only considered, and if you uh, multiply, means if you put the shear stress is 0, then you will get only this under square root of zero point 0.5 up to this only normal stress kind formula. So this maximum principal stress set you can use for a brittle material, and the main concept is a factor of safety. The basically factor of safety is limit stress value of material divided by maximum on basis stress. Means limit stress value for the material, for ductile material we will consider it as a yield point, and for a brittle material we will consider as a ultimate tensile stress. So these both divided by one basis stress means which whatever stress you will get, you can simply uh, divide that stress by yield stress, so you will get a factor of safety. And there are three assumptions in static analysis. First one is a response is proportional to the applied load, means if you get any deformation for particular load, and if you double that force, then deformation also get double, means the linear assumption is there. Then material will be elastic, that means if part return to original shape, if loads are here, means if you remove the load, then part return to its original shape. And last one is a load are a static, means you can't apply here a gradual or impact load. Here load are applied only slowly or gradually. So finally here checklist of your SolidWorks simulation. First you need to check a material, then you need to check a physical conditions, the pressure, force, fixture, whatever they are holding you and everything. And after that you can perform the result. You can predict that the factor of safety and stress or you, and you can say that your design is safe or not. So that's it for this session. This is all over the introduction about the static part of SolidWorks simulation. In next session we will start with the simple uh, simulation, and we will continue this series afterwards. So thank you friends. I hope you have understand whatever I explained you. So kindly let me know if you have doubts. Please thank you for watching this video, and like, share and comment as well. Thank you.